Hello once again, this is presentation 7.6. The topic is the t-distribution, inferences from small samples when sigma, the population standard deviation, is unknown. We want to recognize the development team of Brad, Spencer, and Amanda. And we're going to use an illustrative example here on the screen. We have a case where a tobacco manufacturer makes the claim that the tar content of its cigarettes is significantly below 6.00 milligrams per cc per cigarettes. A human rights group challenges this and undertake a random sampling of 18 cigarettes from the population. And those data items for n equal to 18, these are the recorded tar content figures. The sample mean standard deviation is given in the lower right here. Now this is sample data or statistics. We want to find a 95% confidence interval estimate of the population mean. And we're saying since sigma is unknown, and when sample sizes are small, for example under 30, we have to use S sub x as an estimate of sigma. And you should try and convince yourself that S sub x is an estimate of sigma for almost all cases. And we're going to look at a student t-distribution whose overall shape depends on what's called degrees of freedom, or n-1. And since n is 18, here degrees of freedom is going to be 17, which was coming up on the screen here. The standard deviation, sigma sub x bar, is now S sub x over square root of n, not sigma, since it's unknown. Because of this uncertainty, we have to use the t-distribution. And the t-distribution is here in the red. We're comparing with the blue, the normal. And for the normal distribution, a 95% confidence interval gives rise to a z-score plus or minus 1.96. And because of the small degree of uncertainty in S sub x as an estimate of sigma, we choose a slightly broader range here, and that instead of 1.96, the t-value is 2.11, and this accounts for the uncertainty in sigma. And we're going to go to the table here now. This is the t-table, and we're going to look at 17 degrees of freedom, going across here. Under the column heading, now this is the area in the right tail. So for 95% confidence, the area in one tail is 2.5%. Coming down that column, we look at the intersection here, 2.11. And now you know where that critical value comes from for the t-distribution. Now we're going to compare the two. Normally you'd use the 1.96 in sigma, but in this case we use the t-distribution in S sub x. And those values are coming on the screen here now, giving us a confidence interval of 5.696 to 6.604. This is a 95% confidence interval for the population mean mu, and since 6 is contained in this interval, it suggests that the tar content is not significantly below 6.00, so they don't meet certain requirements. Now very briefly, we're going to look at another example. Take a sample, 21 people from a large office area of population. Systolic blood pressure, sample mean 128.8 milligrams of mercury, standard deviation 8.4. We want a 99% confidence interval for the population mean. And again, we're going to look at the student t and the normal. For the normal, 99% confidence, the z-score is 2.575. For the t-distribution, we want to look at a larger interval given by the critical values that come on the screen here. Now notice that for 99% confidence, the area in one tail is 0.005. So that suggests that we look up degrees of freedom 20 over in the column heading 0.005, giving us a critical value that you see on the screen here, and this becomes our standard error, S sub x over square root of n, 8.4 over square root of 21, and the confidence interval is given by our estimate, 128.8 plus or minus 2.845 times your standard error, and that gives rise to an interval of 282.25, 286.95. And that's the end of presentation 7.6. We ask you to look at this again and go to presentation 7.7.